Hello, welcome back. This is Calculus by Dr. Oz. Today we're going to go over another application of integration. It's called the volume by using the disk method. We have essentially two learning objectives to achieve for this section, and the last learning objective is sort of like optional. I'm not going to keep you responsible for that, but if you're interested about that learning objective, please check the lecture notes. In the first video, we're going to try to go over the first learning objective, which is finding the volume of a solid of revolution using the disk method. And in the second video, you will see how we're going to tweak that formula to come up with the volume of a solid of revolution using the washer method. All right, let's get started. All right, let's get started with the disk method. So I'm going to show you this representative picture first to be able to explain what I'm going to do next. So normally we start with a representative rectangle as we did in the previous section. And in this section, what we're going to do is to not find the area of this rectangle, but we're going to revolve this around the x-axis, let's say, and we're going to get this disk here, as you see. And what we're interested is the volume of that disk. And since we have lots of rectangles within the region, within the blue region here, right, then we're going to have a lot of disks revolved around the same axis. So then the sum of the volumes of those disks in the limiting process is going to approach the volume of the solid of revolution, which is in fact what you see in this blue three-dimensional graph here. So let's go back and talk about what means to have a solid of revolution. So let's say like we have a region in the plane, and that's a rectangular type region with height r and width w. Okay, so this line here is called the axis of revolution. What we're going to do is to revolve this this area here around the axis, and then we're going to get this nice disk type object. Okay, and this is called the solid of revolution. Okay, and the volume of this kind of like disk is known by pre-calculus. We know that it's like pi r squared, because the radius is r, times its thickness. So the area of the circle times the thickness of the disk, which is w. So okay, so we have the volume of the representative disk. What we're going to do is just to write down what that is exactly. Okay, so it's pi times capital R squared times w. But as I showed in the first picture here, that we have lots of those disks obtained by revolving rectangles within the region about the axis of revolution. So therefore, the sum of the volumes of those disks is represented here. So you have the summation formulation, pi times r of xi quantity squared delta x. And as you see in this graph, that those radii here are determined by this curve. So whatever this curve is, that's going to tell us exactly what the radii should be. So essentially, we just say like this radius is determined by the point where you are within that region. So that's why we use this kind of like representation. So the sum of the volumes is going to be the approximation of the volume of the solid, and we need the limiting process like we had in the previous section to come up with the definite integral representation of the volume, and that's essentially letting n go to infinity, or letting the length of each subinterval go to 0. Okay, so that takes us all the way to pi times the radius, which is a function of x, squared times dx from a to b. So essentially, here's the process again. Let me just quickly describe that. So you have the known pre-calculus formula, which is the volume of a disk. We know that formula, the area of the circle times the thickness of the disk. And then we have the representative element, okay, representing just the volume of one solid of revolution, which is a disk in this case, and then passing the limit to get this new integration representation or formula of the solid of revolution. And this is kind of like the revolution about x-axis. Just to sum up, you just get this representative rectangle, and then you just revolve this around, you get a representative disk, and then that disk, the formula for the area of that disk is going to tell you exactly how the integral corresponding to that should be. And in fact, it's in this case, it's integral from a to b pi times r of x squared dx. So what if we revolve around a vertical axis, not a horizontal like x-axis type axis, but a vertical axis, maybe y-axis? Well, then we're going to have a representative rectangle, which is in fact perpendicular to the axis that you're trying to revolve. Okay, so as you see that this rectangle is perp to the y-axis, and then you just revolve it around the axis of revolution, and then you get a disk at the top. Okay, but now the thickness is not dx anymore, but dy, and r, the radius of the representative disk is a function of y, because so this rectangle sort of like is moving up and down instead of right and left. So then you're going to represent this volume by a y-dependent integral, as you see here. So it's essentially the same formula, but then the limits would be c and d, which are the limit values in the y-axis to define that region, blue region. And the formula goes like pi times the integral from c to d, r of y squared, because r is a function of y, okay, times dy. So again, depending on the context, depending on how the functions are provided to us, we can also use this type of formula to come up with the volume of the region revolved around a vertical axis, not a horizontal axis. All right, let's have an example just to apply this formula. Let's say like we have the function radical sine x, and we have the region bounded by this function and the x-axis, but just partially the part of the x-axis from 0 to pi. So we're talking about this blue region here. And what we're going to do is to revolve this region around x-axis. So this is the axis of revolution. And you get a football type object, three-dimensional object. And what we're interested in is to come up with the volume of this football. Since the axis of revolution is the x-axis, so we're going to get a representative rectangle perpendicular to the axis of revolution. And then we just revolve this around. Let's say like this representative rectangle comes with thickness dx. And let's say like this is just x units far from the left end of the region. So then, since this function is radical sine x, the height of the rectangle, as you see, touches the curve radical sine x. So that determines the height of the rectangle, which is in fact radical sine x. So in other words, r is just f of x. And now let's use the formula. Essentially, v, the volume, is equal to pi times integral from a to b r of x squared dx. This is the disk method. And the lower limit is 0, upper limit is pi. And the function is radical sine x. Here we go. So let's just do this part together. Pi times integral from 0 to pi. Radical sine x squared is just sine x dx, and if you integrate sine x, and that is a negative cosine x from 0 to pi. First, we're going to substitute the upper limit, so it's pi negative cosine pi minus, we're going to Substitute the lower limits. Pi times negative cosine 0. And go ahead and use your calculators, or if you know those values, just simply uh, use that knowledge. So cosine pi is negative 1. So negative 1 is plus 1. So this is pi. Okay. Cosine 0 is 1. So this is negative 1 then. So negative 1 times negative pi is just pi. So that takes you to the volume exactly equal to 2 pi. And whose volume is that? And that's the volume of the food bowl mentioned in this example.